There's been a few questions about this particular question where we're shown part of the radio spectrum and we're asked to identify different types of channel degradation in the frequency domain. So let's look at the spectrum bit by bit. So from left to right, what we have here looks like two identical sidebands. So that looks like what we would call DSB. And because there's no carrier component here, we call that DSB suppressed carrier. So you have an upper sideband and a lower sideband. What we see here around 120 kilohertz is probably the same. It's not certain, but it's probably, again, DSB suppressed carrier. So there isn't a carrier term here. So we probably just have an upper sideband and a lower sideband. And what we have after 200 kilohertz looks like AM with an upper sideband, a lower sideband, and a carrier. And it's a single tone AM, so the message is a single sine or cosine. So that's just AM. Now, if you look at the spectrum, the spectra in real life are never perfect. So what the original spectrum might have looked like might have been something like that, but due to channel degradation effects, they don't look perfect. So if that's our first signal, we see that the spectra of the upper and lower sidebands are not identical. They're asymmetric. So there's this component here. So something is wrong. So what kind of channel degradation effect is that? So that's what we call interference. So it's some frequency around 85 kilohertz that's interfering with the lower sideband. We don't see the same thing here, so it's clearly not part of the original message. So it's something that's interfering with the signal, and that's come from the channel. So that's a channel degradation effect. Now, if we look at our next spectrum, which we're guessing is DSB, then the original spectrum might have looked something like that. And again, the upper sideband and lower sideband, they're not perfectly symmetrical. So something's going on here. And that is what we call distortion. It's where something has happened to the signal. There's been some change in the signal from what it was originally. So along the channel, something happened to the upper sideband to make it different from the lower sideband. And if we look at the final spectrum, the AM spectrum after 200 kilohertz, so we have a carrier component, we have an upper sideband, and we have a lower sideband. But here, this is what we call white noise. So this is what noise would look like in the frequency domain. So we've got an interference component, we have distortion, and we have white noise, all affecting the spectra in different ways. Now you might remember that we looked at each of these channel degradation effects in our Cahoots class. So if you remember, we looked at this DSB spectrum, and we said, well, the spectrum shown, we've got a lower sideband, an upper sideband, but something's going on here, and we said that's DSB with interference. So that's almost exactly the same as what we have here. And then we looked at this spectrum here, and we said that this is AM, because we have a carrier component, we have an upper sideband and a lower sideband. But what we're looking at here is white noise. Sorry, where is it? White noise. So again, that is exactly the same as what we have here. So the actual shapes of these spectra and how interference and noise and distortion affect our spectra isn't entirely new. We have covered this before. And if you look at this spectrum, even less neat, we have a whole load of things going on. So we have this is probably single sideband. That might be the carrier, or that might just be an interference term. Again, here it looks like we have DSB. That looks like it's interference. But the question, what we were actually being asked about, was this. We were told that the carrier frequency was 140 kilohertz. And we were asked to select the component that's causing the most damage. So if you look at it, we have a tiny little carrier component there. That's not really a carrier component, because AM would never have such a small carrier component, because the modulation index would have to be bigger than 1. So what we're looking at here is two interference components. 1, 2. Now the interference component at 140 kilohertz, that translates to DC after demodulation. So that's not a problem. We can eliminate that easily. The dangerous one, the difficult one to eliminate, is the one that's actually contaminating the sideband. Because remember, the actual information is in the sidebands. So a small carrier component doesn't really affect it. It'll make it look like AM that's been overmodulated. Our problem is with the interference component. So remember, spectra, radio frequency spectra, they never look perfect. They'll always look very messy and ugly, and all of these components, all of these different effects will manifest. So it's slightly disappointing to find many people struggled, in particular with this one here, with the distortion. So this here is not distortion. This is an interference effect. And we've spoken about that before, and we played a video about how interference was identified. And this here is white noise. That's exactly what white noise will look like in the frequency domain. So I hope that has helped clarify some of this, and I hope you found this video